All right, let's take a look at our lesson for today. We're actually going to introduce optimization problems. These are word problems that we'll be working with. And this first lesson is an introduction to them. So what I'd like to do is go through the process, how we will solve these, and then we'll jump into examples. So these type of problems, the optimization problems, we have a process that is recommended that you use. And so here's the process. We would draw a picture, if it's a geometric shape, we would draw a picture and we would identify the quantities we know, and give a variable. So we would want to assign a variable for unknown quantities. We would write an equation that we want to optimize. And what optimize means, it means like maximize or minimize. That's what optimization means. We're going to be maximizing or minimizing a quantity. We need to get our equation in terms of one variable. This is significant. Just one single variable. And so with that, what we will probably have, or what we will have if we have more than one variable, is we would have a helper equation. I call them helper equations. The helper equation will allow you to get rid of a variable. So a helper equation allows us to get rid of a variable. Okay, so then we would determine what the max and min are with our calculus techniques, and the calculus technique that we will use is candidates test. Okay, so that technique is going to be candidates test. Then what we do is we determine the numbers that are the candidates. These are the candidates. It's the domain, so the endpoints. We're looking at the endpoints, and we're looking at our critical numbers. The domain and critical numbers. Those are the candidates. So that's the process that we will use every time that we work an optimization problem. So I'm just going to go over it one more time. We're going to draw a picture, identify the things we know and the things we don't know. We'll assign a variable to the things we don't know. We're going to write an equation that relates all those variables together. And we will write an equation for what we want to optimize, maximize, or minimize. We get our equation in terms of a single variable, which we may have a helper equation, and that allows us to get rid of a variable. Okay. Then we would find our max or min using calculus techniques, which is candidates test. And then we would, this is part of 4. We would need our candidates, which are the endpoints and the critical numbers. Okay. So that's an overview of the process. Are there any questions on the overview of the process? Okay, so let's, what we're going to do in these examples, numbers 1 through 4, we're only going to the location, all the way to where we're writing the equation that needs to be optimized. We're not going to solve yet. We will solve these types of problems in the next lesson. Okay, so this is like a preparatory lesson. We're just going to get it ready to solve. And just a reminder, the equation that we write has to be in one variable. We really do not have a choice. It must be in one variable. All right, so let's look at our first example. So we want to find two numbers whose sum is 30 and whose product is as large as possible. These are the words that we're looking for, large as possible. This tells us what kind of optimization we're doing. Large as possible means that we are going to maximize our equation. Large as possible means maximize. So let's see what information we have. We really need to pick apart the words. So we're going to find two numbers whose sum is 30. I'm going to write something for that. So I'm going to say I've got number X plus number Y is 30. So there's my two variables. I'm just Just pick, you can pick whatever variables you want, but I just chose X and Y. And the other criteria here is whose product is as large as possible. This is the piece. Product is as large as possible. This is the important equation. This is the equation that we're going to maximize or minimize. So we need to write an equation for a product. So what we would do is I would just label it product equals, and then I would multiply those two variables. Okay, so this is the main equation. This is the one we're going to optimize. So that makes this one our helper equation. This is our helper equation. We must need it for something. It's our helper equation. We can only have one main equation, okay, just one, and that has to do with what we're optimizing. So the other equation or equations would be called helper equations. So since our rule is to only have one variable, can we see how our helper equation would work? We would take our helper equation and we would solve it for either X or Y, it doesn't really matter. And then we would use that to sub into our main equation. Okay, so I chose to solve for Y. Like I said, it doesn't matter. So I solved this for Y. Y equals 30 minus X. And then what I'm going to do is I'm going to take this right here and I'm going to put it right in place of the Y. I'm going to get rid of the Y because, again, we can only have one variable. So let's redo that. So our main equation would be product equals X times 30 minus X. So we're going to, when we get to solving these, we will be taking the derivative of our main equation. So let's just kind of get it cleaned up so our derivative is as easy as possible. So let's distribute. So I've got 30x minus x squared. And this is the equation that we will maximize. So let's just write ourselves a note. So again, today we're not going any further than this, but this is the quantity that to be maximized. So this example took us through all of the parts of an optimization problem. We didn't have a figure to draw because it was just numbers. All right, questions on this process? Okay, so in the next lesson, we'll continue on with this. We'll actually maximize that, but that's in the next lesson. Today, we're just setting them up and getting comfortable with that. All right, so let's take a look at our next examples. So number 2, what point on the graph of y equals square root of x is closest to 5, 0? Now, I'm just going to draw a graph. Okay, so we can kind of see what's going on. We're going to draw our, let's see, the square root of x, you know, kind of looks like this, right? Let's see, so it's 1, 2, 3, 4, 5. So 5, 0. So we're looking at this point right here. We want to know what point is closest. So I'm just going to, you know, pretend maybe a point around here, you know, somewhere around there would be closest. Okay, so we don't know, you know, somewhere. That's what we're looking for. We're looking for the point that would be closest to 5, 0. Okay, so let's think about what that means. So first of all, closest means minimize. So closest to, this is something we're going to minimize. We're going to minimize. And so we need to think about what kind of an equation could I write that would help me determine close. That would help me get close. Close is like if we think about it in overall, it's like a distance, right? If I were really going to, like I was going to do an experiment, I would put that point several places and I would measure, right? I would measure the distance. So we do know an equation that helps us measure distance. Remember that? on our formula quiz, distance formula. One of the reasons that we're working, memorize that because we need it. So I'm just going to write the general equation here. So remember, it's x1 minus x2 squared plus y1 minus y2 squared. That's our general equation for distance. This is a distance. So our distance formula. Okay, so now let's substitute in the information that we have. When I'm using a distance formula on optimization, and it happens, you probably will, I make the point my x2, y2. The reason that I do that is I would rather subtract a number than a function or a variable. So that's just what I do. You don't have to. I mean, that's just what I'm going to do. So let's sub in that point in our distance formula. And so that would be x minus 5 squared plus y minus 0 squared. Okay, so we sub the point in, and now we don't have to do the whole x1, x2 things because, we have an x and a y. Now, I'm only allowed to have one variable. I have two. So I'm going to have to go back up to the information and see if there's something that I haven't taken into account yet. Is there a helper equation? This is our main equation. This is the main equation. This is the one that we're going to optimize or minimize. This is the main one, but we need a helper equation because we can only have one variable. So do you see an equation that we haven't used yet? This equation right here, we have not used it. I mean, we graphed it, but we haven't used it in our work yet. This one is our helper equation. So how am I going to use my helper equation? I'm going to replace either the x or the y down in my distance equation. What would be the easiest one to replace? It's already solved for y, so wouldn't that be the easier one to replace? I mean, you can choose whichever one you want, but I'm going to make it easy on myself. I'm going to replace this y with this. I'm going to take the y and I'm going to make it the square root of x. I'm going to sub that in so that I get down to one variable. So the distance is x minus 5 squared plus the square root of x squared. Now this is what we're going to maximize. We're going to have to take the derivative of it when we work it eventually. So let's clean it up a bit. That's a bit too much. So I would FOIL this out. That would give me x squared, minus 10x plus 25. And then the square root of x squared is just x. And then again, I'm just cleaning it up, getting it ready to take my derivative. So I've got x squared, minus 9x plus 25. And this is the equation right here that we would maximize. So this is to be, because we're doing what are we doing? We're minimizing, we're closest. This is to be minimized. And that'll be in the next lesson where we would continue that. All right, questions on this setup? Okay, so we're really experiencing several different types of optimization problems that we will encounter, and we're working on how to set them up. All right, so let's look at number 3. So it says Mr. Kelly needs to make an open top box to store all of his magic cards. He has a piece of cardboard that is 14 by 30. To do this, he cuts out squares of equal size from the 4 corners so the 4 sides can be bent upwards. This is a classic kind of problem that you would encounter. What size should the square be cut in order to create a box that with the largest possible volume? Here we go. Largest possible volume. Those are the keywords we're looking for. So what are we trying to do? Are we maximizing or minimizing? We're maximizing. So we're maximizing volume. That's going to be our main equation is going to be a volume equation. All right, so we need to draw a diagram because I mean, this is a lot going on. I need to write some stuff down. So here's my piece of cardboard. This is 14 and this is 30. We're going to cut squares out of the corners. So I'm going to make it like little dotted lines. I'm going to call those X. So we're cutting squares out of the corners, out of all the corners. So we'll just indicate that with our little dotted lines. Okay. Let's see. So we are looking at volume, and this is going to be like a three-dimensional figure, right? It's going to be like a box. So the volume would be, we probably should know those volumes is length times width times height. Right? That's what the volume is. So let's use that on the figure that we have right here. So let's think about what would the length be. I'm going to call this part with 30 the length. I need something to represent this distance over here, which is not going to be actually 30. It's going to be 30 minus what? What would I take away from this side? 2x, exactly. This would be 30 minus 2x. That would be my length. Okay. All right, let's look on width. Let's consider this our width right up here. So if I'm going to write an expression for width, it's not going to be totally 14. What's it going to be? 14 minus 2x. Okay. My height, if you can visualize this, when these corners are cut out, this box is going to be folded. I'll just make like a little folded. It will be folded right here. Right? That's going to be, this piece right here would be folded up. And so what, on this figure, what variable would we use to represent height? X. We would use X to represent height. And that's the equation that we're going to maximize. Now, again, we're going to have to take the derivative of this. So it would be in our best interest to make it as easy as possible for ourselves. So I would FOIL everything out so that my derivative work is easier. So 30 times 14 is, now if you had a lot of big numbers like this, we would probably give you a calculator, but I mean 30 times 14 isn't too bad. 30 times 14 is 420. And then what are we doing? 30 times negative 2x is negative 60x. And negative 2x times 14 is negative 28x. And then negative 2x times negative 2x is negative 4x squared. Okay, and that's still, we got to still multiply by x. So we've got, what do we have? We have 420x. Let's combine 60 and 28 together. What would that be? That would be, what, 88? So minus 88, and x times x is x squared. And then, say that again? Yes, it's added. Thank you. It's added. And so then we, whoops, that one was subtracted. Then we do 4x times, 4x squared times x would give me a 4x cubed. Now this is, again, we're stopping, we're not continuing. Actual optimization problems would continue on, but this is to be maximized. And to be honest, the hardest part of optimization is getting this far. Once you get your equation down to one variable, it really is pretty straightforward. And it's things you've done before, you know, derivatives and all that. But getting this far is the most challenging. So it's good that we're practicing this separately. Okay, we okay? All right, one more optimization problem to set up. So we've got two towers that are 30 feet apart. One is 12 feet high and the other is 30 feet high. I'm going to stop at that sentence and I'm going to start sketching. This is a lot to take in. Okay, so we've got this deal going on. So this tower is 30 feet high and this one is 12 feet high. Okay, let's keep reading. wait, no, the 30 feet apart. The tower is 28 feet high and 12 feet high, and that whole distance is 30. Okay. There's a stake in the ground between the towers. Now, it doesn't tell us where the stake is. So I'm just going to guess. I mean, it doesn't really matter. I mean, I'm going to put it right here. Okay, the stake is right there. It's somewhere between there. We don't know. The top of each tower has a wire tied to it that connects to the stake on the ground. Okay, so let's stop there. So we've got a wire, and the wire is from the top of the tower to the stake. And I guess it's, I don't know, making it more stable. I don't know. So there's a stake in the ground between the top of each tower has a wire tied to it that connects to the stake on the ground. Where should the stake be placed to use the least amount of wire? Least amount of wire. Are we maximizing or are we minimizing? We are minimizing. We are minimizing. Okay? And we're minimizing the length of the wire. This light blue, we're minimizing that light blue surface. Okay, so we need some more variables because we don't even know where that stake is. So why don't we make this X? I'm just going to make the smaller one X just for ease. If that one is X, then what is this section of this length? What would this be? 30 minus X, very nice. It would be 30 minus X. Okay, great. Now, what I'm going to do, I need to assign a variable to each piece of that wire. And so what I did, again, you can choose whatever variables you want. What I did is I called this one wire 1 and this one wire 2. And that's how I did it. Again, you can choose A and B if you want to. Okay, so the total wire is wire 1 plus wire 2. Okay, and the total wire is what we want to minimize. Are we okay? So we want to minimize the total wire. The total wire consists of wire 1 plus wire 2. So now what we need to do is come up with a way to express wire 1 and wire 2. So I'd like for you to consider what this is right here. And how could I write, and we're going to treat them separately, right? These are two different ones. How could I write some kind of expression that would combine wire 1 plus these quantities? What could I do? What formula could I use? Pythagorean theorem, absolutely. I could use Pythagorean theorem. So let's just make some sketch work right here. So this would be 28 squared plus 30 minus x squared equals wire 1 squared, right? That's what that would be. And so wire 1 would be the square root of all that mess. Oops. Okay, that's wire 1. Are we okay with wire 1? Okay, so that's our and what we're going to do is we're going to take this and we're going to put it right there in just a moment. We're going to sub that in for wire 1. Okay, let's work on wire 2. So we need to figure out a way to represent wire 2 with this information that's in this triangle, and I agree we would use Pythag again. And in this scenario, we would say x squared plus 12 squared equals wire 2 squared. So wire 2 is going to be the square root of x squared plus 12 squared. And then we're going to take that information and we're going to sub it in right here for wire 2. Okay, is everybody okay? All right, so let's do that. Let's go ahead and sub that information in. So I've got the wire equals, let's write down the expression for wire 1. That would be the square root of 28 squared plus 30 minus x squared plus the expression for y2, square root of x squared plus 12 squared. And we are not going to try to simplify that. This would be a calculator question. So this is the quantity that we want to minimize. This is what we would use. It would be to be minimized to finish this problem. Okay, how are we on our intro to optimization? We okay? Okay.